Now we want to, the next topic is a little bit old, a bit, I mean, this is, because we skip a lot of chapters, so there's a certain section talk about the Stanlow theory. And, well, actually, it's just identified as some kind of, you can erase all those. We just divide this. It's just identify the language of this one. So basically, this is expansion. You can actually say that this is expansion using some basis, but this is using exponential function as a basis, and this series is using sine and cosine as a basis, right? And this basis are defined over this period. Okay, and now this kind of integral is like using it's uh, using the language of this series, like the scalar product. You can define like the textbook, define a scalar product between two functions as integrate over the domain. That's a complex conjugate of that. And then, so this is like a scalar product between between the function f and the basis, and except that now this f is this g. Actually, I should reverse that, but that's how you write it in your textbook. But anyway, this C sub n is like C sub n. It's like defined as your a scalar product of the the function that's not this the f is here, and then this becomes the basis because there's a complex conjugate. This is a complex conjugate. The basis you can say is phi sub n, except that this is not normalized. When you normalize this one, you introduce a square root of 2 pi, and so that is that you and the square root of 2 pi. Right. And that using this definition and all this phi sub n, the 1 over square root of 2 pi e to the right. For the compact series, these are your basis functions. And we introduce this normalization such that it's so-called orthonormal. So phi m. You can just use this definition, and the definition of phi, and then definition of scalar product is 1 to 2 pi integrate e to the I m minus n. But you just use this definition. Change phi n has a complex conjugate, becomes minus, right? And phi m is just directly copy here. You do the integration like that, and that is obviously we did that before. How you divide that? This is a conical delta n. Okay, it means that it's 1 when n equals to m, and 0 when n is not equals to m. So this is called this condition is called the orthonormal condition. Yeah. Yeah, I continue to do that. This is just all right. Yeah, this doesn't stop me. Yes. Okay, good. It's just writing it too quickly. All right. And so that's the orthonormal condition. Okay, so these spaces are which we chosen it to be orthonormal. And likewise, you can write down the same orthonormal condition for all the cosine and sine. I think your textbook choose all your phi differently for the sine and cosine series. So for the sine and cosine, phi 0 is chosen as this. This is exponential function for sine and cosine. Phi 0 is it's just 1 over square root 2 pi, and then phi n. Choose positive n as cosine, pi minus n is the sine. Now using the same definition of the scalar product and using this form of your basis, you can convince yourself this is also orthonormal. So it's like sine, like it is n and minus n. One is sine, one is cosine. The integration over a period is 0, like what we did. And also 0 to all the finite n. Also is 0 because you just integrate over a period of a periodic function. So that is 0. So only situation when it's non-zero is you have cosine square of this is so phi n square, so cosine square divided by pi, integrating over 0 to 2 pi, and cosine square, that integration gives you 1/2 of the period, so 1 to pi, cancel with the pi, give you 1. And so the same condition apply for if you choose a basis like that, or you choose your basis like that. Is that okay? Yeah. That is the complex of the here. But the phi is different. This is just phi is just arbitrary notation. So this is a set of this is one set of the choice of basis. This is using exponential function as a choice of basis. This basis is using sine and cosine. Okay. Like, you have f of x. The first question. This one. Yeah. Then you have that. So the f is a complex. But this is again. This is the definition. This is arbitrary f and g. This is not related to this f. So whatever f and g, you define your scalar product using this integral. This is mine. It's just this is choosing n is from other than 0 is n. You just chooses you just so that you just separate the cosine and sine using positive index and negative index. So you can run through all your integer this way. And okay, so it doesn't matter. It doesn't have to be. You can choose your basis. Just half of that is also fine. Later on, we see that using cosine sine series and cosine, Fourier sine series, Fourier cosine series, right? But that's just in terms of the language of this Stern-Liouville theory. And if we define this basis function, those basis functions satisfy this orthonormal condition. Okay, but we have a few minutes left, so before we go, once we have this, there's another relationship. We can use the basis function to write it out, and that is so-called completeness. The completeness is basically the assumption built in when you do the expansion. You're just basically saying that for a function defined over your domain, in this case, a 2 pi, and you can expand that using this basis, either exponential basis or this sine and cosine basis. This is a statement that needs to be proved, and the proof is slightly more complicated. And just saying mathematician has proved that they actually can be done. So that is so-called completeness. If it can be done, it's a complete this basis form a complete set. So all these exponential function bases form a complete set. And all this, if you define this way, also form a complete set. And so that's just the way you call it. But there's a relationship coming from the completeness condition, and you can see it. You can see it by say like substitute all the c sub n back to here. I think I'll just do the c sub n. I'll leave the sine and cosine sine series and cosine series. It's just basically the same. But we substitute this into here. So the equation you get is fx equals the sum n minus infinity to infinity. Substitute c sub n, this expression into here. But when you do that, you need to be a little careful because this x is your integration variable, is a dummy variable. You can, because you already have x here, so you need to choose another dummy variable in order to not cause confusion. This is, I can see it but this stuff. Need to be a little careful. And now you have a fx prime, call it another name, e to the minus I n x prime dx prime. Right, and then you copy this down. You already have a dx. Okay, right. And now you can rewrite your expression, put the integral out, and do the summation here, and bracket. And now you have the e to the I n x minus x prime, right? And then f. Okay, this is group that is exactly the same thing. We group that. So you see that there's the form of this integral is like you integrate over the domain, the same function that you want to explain, multiplied by something, you get back the same function. And the notation we this could be done is called a Dirac delta function. This is delta. Okay. Have you learned Dirac delta function? We haven't learned. Some of you learned Dirac delta function. So Dirac delta function is basically defined over integral. So you have so delta x minus x prime dx prime and fx prime. Any integration domain that you integrate over, if this from A to B contain the point x equals x prime, then this is fx. If x is within A and B, right? And then 0 C is outside this range, so you're 0. So this is what it is, right? That's how you define and Dirac delta function. So you can integrate just a little, like integrate A and B can be just x minus a little bit or x plus a little bit, as long as this range contain x equals to x, x prime equals to x. Okay, that will give you f. And of course, there's some smoothness assumption over fx. Fx is not something that just like fluctuating crazy, right? So if fx is smooth enough, and that's how you can define the delta function. We'll probably have another chance to talk more about delta function, but that is how you express this kind of situation. So basically, now the complete or the consequence of a completeness is this relation of you write down more explicitly using our basis. You use our basis. The basically is sum of n infinity to infinity by n complex conjugate of x prime Prime n equals to the yes. Okay, so this is using this definition of your basis for your exponential function basis. And so you can write it like you can write it either this one equals the other function using your orthonormal basis. You can write the completeness condition like that. Okay, so that is something that um, uh, useful in many cases. Especially when we do some problem, you have a delta function. I mean, this you can say that this is like a expand a delta function using this Fourier series, right? So delta function, if you treat it like a function x, although your x prime becomes a parameter, put it in here, and so this summation is like a Fourier series, right? Except that not all our coefficient now has this x prime as your parameter, which turns out to be exactly the basis in the complex conjugate. Okay, so that I mean, either you can look at this as a consequence of your completeness, or as like you expand the delta function using your series expansion. Okay, so but it's useful in many cases, especially when you solve differential equations. Sometimes we use that because we use delta function quite a lot. You know how to expand your function. Delta function is in orthonormal basis. That's useful. Okay, we'll continue then. Any questions for you? Because we are out of time now. Is that okay?